In this video, we're going to take a look at our peak time and percent overshoot parameters to help us describe our waveform for our underdamped second order system. So as we had in our last video, we had this response C of t, and what we're going to do first is look at our peak time T sub p. And so the peak time is defined as the time required to reach the first or the maximum peak. And so what our peak time is doing is it's a metric for the speed of the response. So if we come up here to our plot, we can indicate our peak time would be right about here. So I'll draw a dashed line down to our time axis, and this would be our peak time T sub p. And my axis isn't quite high enough, but the corresponding value of C would be our C max, so our maximum value of C. So how can we calculate an analytical expression for T sub p? So take a minute and maybe think about that before coming back and watching the rest of the video. So how to find TP. And again, we're looking for an equation or an expression, not just a single value. So in order to do that, we can consider this equation. This is equation 1 from the previous video for our C of t. And so you might remember from calculus, if we want to find the location of maxes or mins, a good thing to do is to take the derivative of our time function and set it equal to 0, and then we can solve for t. So let's say we can take the derivative of C of t, set equal to 0, and from there that will give us our local maxes and mins. And it should be pretty easy to distinguish which one is that first one near TP. However, if we take a look at the C of t equation, it's kind of messy. We've got this exponential, we've got this cosine term, we've got square root of 1 minus zeta squared floating around in a couple places. So it's really not going to be too fun to take the derivative of that. But we have an easier alternative. So instead of doing that, what we can do is we can work in our frequency domain. So in the frequency domain, remember we're utilizing our Laplace transform. And so we had talked about in a previous unit our Laplace property of differentiation, or our time differentiation property. So time differentiation. And so what that property was is if we're taking a derivative in time, we just multiply by s in frequency. Now we're going to assume we have no initial conditions to say that basically if we want to do d C of t dt, then that's going to correspond to multiplying by s in our frequency domain. And so in the previous video we had an expression for C of s, so essentially our multiplied s here is going to cancel out with the 1 over s from our step function. We're not going to go into the details of doing that, but hopefully you can see how this approach using this Laplace transform property is a lot easier than taking that derivative in time. If you want to see a little bit more details on that, you can look on page 148 in the 8th edition of the text, but we're just going to write the result here. So if you go through that process, just a couple lines, you get T sub p, our peak time, is equal to pi divided by omega sub n times the square root of 1 minus zeta squared. So let's call this, to be consistent with my notes, equation 2. So now we have an equation, a generalized equation, where we can find this peak time T sub p. So another important parameter that we're going to use to characterize this response is our percent overshoot. So our percent overshoot, often I'll just write percent OS for percent overshoot. And what this is basically the amount that the waveform overshoots that final value. So amount the waveform overshoots C final, or as I have it labeled above, just C sub f. And of course that's occurring at our peak time T sub P, and it's a percent, so it's going to be expressed as a percentage of our CF. So expressed, got an extra S floating in there, expressed as percent of our CF, our C final value. So to be consistent with the previous video, let me just get rid of that. So we're talking about CF everywhere. And so our CF is, of course, our steady state value. What does the value go to as time goes towards infinity? So let's just get a basic definition for our percent overshoot. So our percent overshoot equation is going to be C max minus C final divided by C final times 100. So just based on our basic definition that we have written above, that's what we have for our percent overshoot. So let's sort of refine this a little bit. So how can we figure out what this C max is? Well, if we come back up to where we were talking about our T peak, we see that our C max is the value that corresponds to T peak. So what we can do is we can basically take the TP value and substitute it into our equation 1. So if we substitute a TP here, then that's going to give us our C max. So let's come down here and just write that. So our C max is equal to C evaluated at T equals T peak. And of course our T peak is coming from, the value of that is coming from equation 2. So let's just write TP from equation 2, and of course we're plugging that into equation 1. Now for this case our C final is just going to be 1. So C final equals 1 because we had the unit step response, and as we saw in a previous video, if we let t go to infinity in this equation 1, we have this t and this decaying exponential, so that term's all going to go to 0, and we're going to be left with just this 1 here. So C final is going to be 1. Okay, so we can plug these values in, and what we get is that our percent overshoot is equal to e to the negative zeta pi divided by square root of 1 minus zeta squared, and all of that times 100. Okay, so we've skipped some of the sort of detailed math of that, but as long as you understand the basic process, and ultimately as long as you can use these equations, you'll be good to go. So one thing to note looking at this equation is that our percent overshoot is only dependent on that damping ratio. So only dependent on the zeta, because our pi, of course, is a constant value, our 100 is a constant, we have 1 exponential, so all of these things are just fixed values. The only thing that's going to vary is our zeta. So what we can do then is we can solve this equation for our damping ratio based on our percent overshoot. So if we do that, we get that our damping ratio is equal to, in the denominator we have the square root of pi squared plus the log, natural log squared of percent overshoot divided by 100. And in the numerator we have negative natural log of percent overshoot divided by 100. So both of these equations can be useful depending on which parameter you're looking for, damping ratio or percent overshoot. One other thing that we can note about these two items is that if we're increasing our damping ratio, we're going to be decreasing our percent overshoot or our rate of oscillation. And so coming back up to this figure, what that means is that essentially we're going to be decreasing how far above this overshoots here. So those are our two sort of our peak value and our percent overshoot. So in the next video, we're going to come back and look at our other two values, our rise time and our settling time.